So here we're going to look again at graphs and think about what kind of stories we can tell them, or tell from them, or tell with them. So this time we're specifically going to look at straight line graphs, or linear graphs. And there's a few key features that we'll always want to be talking about. The y-intercept is where the line crosses the y-axis, or the vertical axes. Because again, in some cases it might be referring to matchsticks or distance, but it's always going to be, we can think of this as the y-axis, even though in this case it's really referring to d or distance, but it's the vertical one. So specifically here, the y-intercept for the blue line is going to be equal to 4 in this case, because it's crossing the line here, it's going through it at a value of 4. So the y-intercept here is when y is equal to 4. And for the red line, the y-intercept here is going to be, let's be careful about the scale. We have to check to see how are these going up in. If I went 1, 2, well that doesn't work because 2 is supposed to be up there, so how can I count from 0 to 2 using 4 numbers? Let's try half. Half, 1, 1.5, 2. That'll work. So that's actually a 1. So the y-axis for the red line is going to be when y is equal to 1. So again, it's just when the line actually crosses through the vertical axes. Now the gradient is also known as the rate, and that's telling us about the steepness of the line. It's also always going to be known as the rise over the run, and you can write it as a fraction. So the gradient here always refers to the rate, and it's also the steepness of the line. And for rise over run, we can look at this line and try to decide how far does it go up, that's the rise, and how far does it go over between two given points. So for instance, if I pick this point here, and the next point I pick is here, to get from point 1 to point 2, I have to go up a total of 1, 2, 3, and I have to go over a total of 1, 2. So again, that's going up 1, 2, 3 for my rise, and over 1, 2. So my gradient for the red line is equal to up 3 over 2, or 3 over 2. And for the blue line, start as this is my first point, and I go along and pick another point that happens to be right on top of a line, makes it easy to figure it out. Let's try that one up there. I have to go up a total of 1, 2, and I need to go over a total of 1, 2, 3. So I need to go up 2 over 3. In this case, for the blue line, it's the opposite of the red line, it's up 2 and over 3. Intersections, well, these are points where lines cross. And this means at that point they are equal to each other. So if we look at this graph, our intersection occurs right here where the red and blue line cross. And we can give a point value for that using our coordinate system. Thinking about writing a point as x, y, let's look at that intercept. That's over to 2, 2.5, 2, 3, 3.5, a little bit more than 3.5, so we might say 3.6. Yeah, it's pretty close to 3.5. We'll say 3.5. So at 3.5x and at roughly 6.5, 6.5 on the y-axis. So again, I've gone over 3.5 and I've gone up 6.5 to get to that intersection point. So at that point, the red and the blue line, they're equal to each other, they cross each other. So now if we want to look at this graph, instead of just as numbers and junk on there, let's think about the story that it actually tells. So what I'm going to look at here is looking at and trying to decide information based on the story that this graph gives us. And here we see the graph above, or in this case to the right, shows the distance from the back door in time for two dogs, Lulu and Sparky. And I'll tell you that Lulu is the blue dog and Sparky is the red one. Well, it's not a blue dog, but it's represented by the blue line. So again, showing the distance from the back door and then in time for the two dogs, Lulu and Sparky, when they see their best friend Spencer come into view over the back fence. They run excitedly towards him. So if we want to think about a picture of what's actually going on here, we've got a backyard, we've got a house with a back door over here, so you can imagine that the back door is attached to the yard there. And then we've got a fence over here, and their buddy Spencer, the cat, hops into view along the back fence. And the two dogs, Lulu and Sparky, are in the backyard. They see Spencer, and they run towards the back fence to say hi. So, looking at this graph, let's see if we can draw in where Lulu would be and where Sparky would be. Because the first question is asking us which dog has a head start. So where's the start going to be on this graph? This axis is in time, so it's kind of showing us from the start of time to when they've met Spencer. So you can think about the start being at 0. So at 0, who's closer to the back fence? Because this distance here is the distance from the back door in time for the two dogs, Lulu and Sparky. So this is saying, here's my back door. Which dog is closer to the fence to start with, or which dog is actually further from the back door to start with? We see that Sparky is a distance of 1 meter from the back door. So Sparky is actually going to be fairly close to the back door. And Lulu is actually a distance of 4 meters from the back door, so Lulu's already kind of in the middle of the yard. So looking at that again, which dog actually has the head start here? We could say that it's Lulu. She's further away from the back door, so she's closer to the back fence. She's got the head start towards Spencer. And how is this shown? What feature of the graph, and here I want you to think about, is with the y-intercept? Was it gradient, or was it an intersection point that gave us that information? So if I look at this, how did I know that Lulu was further ahead at the start? And I can see that that is actually because of the y-intercept, where she crosses the line. So the y-intercept has shown us that, because it's a higher value than Sparky's. So y-intercepts can also tell you, basically, things such as flat fees and starting points, depending on the type of context. So in this case, Lulu has the head start because her y-intercept is 4, and Sparky's is only 1. So Lulu is further from the door. Okay, so which dog is faster? Looking at those red and those that red and that red-blue line, which dog actually looks like it's going to be faster? And you can think about things like, how do you describe speed? That's usually how much distance somebody covers in a certain amount of time, like kilometers per hour or meters per second. And that relates to us about the rate or the steepness. And so the gradient also describes for us the speed, because rate is a speed. So if we look at that graph, who actually is running faster? Because if you want to imagine, the back door is down here, and the fence is up here somewhere along that scale. So both of these dogs are running from the back door, in a sense, or from the yard towards the fence. And who's getting there faster? So that speed actually is shown by the steepness of the line here. And we notice that it's going to be Sparky that's fastest. And the feature that is showing this on the graph is going to be our gradient. We could say her line is steeper, so it has a stronger incline, like running up a hill. If you're a little person on this hill, you'd find that red line to be harder to run up than you would find running along the blue line. It'd be easier to run on the blue line. So the harder it is to run up the line, the faster the dog's going. And we see that again as the gradient here. Her line is steeper. So for Sparky, her gradient was 2/3, or 2 meters for every 3 seconds, compared to Lulu, who was 3 meters in every 2 seconds. So Sparky, oops, I've got that the wrong way around. Sparky was 3 meters every 2 seconds, and Lulu was 2 meters in every 3 seconds. So what we're saying is that Sparky can run 3 meters in 2 seconds, and Lulu takes 3 seconds to run even less meters than that. She takes, in 2 meters, takes her 3 seconds to run it, so she's much slower. So can we describe what occurs at about 3.5 seconds, or at about 3.5? Well, if you notice, at 3.5, so 2, 2.5, 3, 3.5 seconds is along here. That's where our intersection happens. And so what does that mean? We've talked about the intersection being the points where the lines cross, and this means that at that point they're actually equal. So this graph is describing the distance from the back door and the time. And at the point where Lulu and Sparky's lines cross, what do they have that's the exact same? They've got the exact same distance. So describing what occurs at about 3.5 seconds is that Sparky, who's been running from behind, catches up to Lulu. Sparky catches Lulu and passes her about 3.5 seconds. So Sparky catches Lulu and passes her at about 3.5 seconds. So again, we can see that because Sparky started closer to the house. She's running really fast. She passes Lulu and gets ahead of Lulu, because now she's further than the house than Lulu. And so that's what we mean here. And this is shown by the intersection. The last question here is, what is the distance from the back door to the fence? Okay. So if we look at this graph again, what's happening is that we notice when they see Spencer, which is here at the start, they see Spencer, they start running towards him, and he's on the back fence. And so the distance here, this axis is showing us how far away from the house they are. So they keep running, they keep running, they keep running. And at some point, what do we notice? They've actually stopped getting any further from the house. So you can imagine maybe in that picture that Spencer and Lulu have run, both of them, all the way to the back fence, and now they can't run any further. So where do we see that happen on the graph? Sparky's running, 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 and then she's at the same distance suddenly. So she's sitting there wagging her tail and sniffing the cat Spencer. So the fence is in fact 8 meters from the house, because we see that they level off at 8. Both Sparky and Lulu stop running any further, and they're just stuck at the back fence at about 8 meters. And what we notice is also that Sparky gets there first, because Sparky gets there sooner in time. Sparky gets to fence. She gets there in about 4.5 seconds. And Lulu does not get to the fence until 6 seconds. So Lulu gets there second, Lulu to fence. And she gets there in second place. And then at that point, they're hanging out at the fence, saying hi to the cat. So the distance from the back door to the fence is 8 meters. And we see that because the line levels off. It can't go any further. So again, this graph is describing how far away from the back door these girl dogs are. We notice that Sparky runs a lot faster because her line is a lot steeper than Lulu's. We notice that they pass each other here. Sparky passes Lulu at about 3.5 seconds. That it only takes Sparky 4.5 seconds to get to the backyard, the back fence, and it takes Lulu 6 seconds to get to the back fence. And once they've reached the back fence, they're hanging out there saying hi to the cat. So this is one way with which we can tell stories from straight line graphs, and we often want to refer to those key features such as the y-intercept, the gradient, or the intersections. So the y-intercept again can be talking about a starting point, or a flat cost, or an upfront fee, like paying $5 to rent a helmet, and then paying an additional amount for every hour. That could also be something like calling out a plumber, and maybe you have to pay him $20 just to get out there, and then he'll charge you $30 for every hour he works. The gradient is also the rate or the steepness of the line. We calculate it finding the rise over the run on the graph. And this refers to the speed, and sometimes also to the cost per hour. So for instance, a plumber who charges $100 per hour is more expensive than a plumber who only charges $50 an hour. So the gradient, or the rate, $100 per hour for the more expensive plumber will be steeper than for the less expensive plumber. And the intersections are points where the lines cross, and this means that they're both exactly equal to each other. So don't forget, we want to think about those 3 key features when you're trying to describe a story on a straight line graph.